Let's see if I can explain this. It says a certain scientific theory supposes that mistakes in cell division occur according to the Poisson process with a rate of 4 per day, and that a specimen fails at the time of the 289th such mistake. This theory explains the only cause of failure. T is the time of failure random variable in days for a newborn specimen. Using the normal approximation, calculate the probability that T is greater than 68. So what we really want is the waiting time until the 289th such mistake. So we use the waiting time from the Poisson summary on page 28 of the summary sheets for MLC. So we want the S289 random variable, and that's the sum from I equals 1 to 289 of Ti. And we're set, the waiting time is distributed gamma with alpha is n, so n is 289, and theta is 1 over lambda, and 1 over lambda is 4 per day here, so it's 1 over 4. So we see the mean is alpha theta, or n divided by lambda, which is exactly what they have here, n divided by lambda. And the variance is n over lambda squared, n over lambda squared. And so now we know the mean of T and we know the variance of T, and so we can find the probability that T is greater than 68 by converting to a standard normal. We subtract the mean, divide by the standard deviation. Subtract the mean, divide by the standard deviation. Look up that value. The other approach was to use this formula down here, and that is the probability that the waiting time is less than T is the probability that the number of events is greater than or equal to n. So in this case, the probability that T is greater than 68 is, if I want the probability that the 289th occurs after time 68, well, that's the probability that I have less than 289 before that time 268. So that's the probability if we have 68 periods, so lambda times the number of periods is 272. That's the probability that we have 288.5 of these in for this lambda t equals 272. So now the mean and variance is 272, and I take n minus the mean divided by the standard deviation, and you see I get the same thing here. I look up at the inverse normal at minus 1. So either way, I get 0.84, answer choice A.